Okay, so we are at lecture 6. It seems like we're going really slow, but slow and steady. So, so we are at we are doing Stirling numbers of the second kind. I mean, the big issue in combinatorics is not really understanding the basics. The issue is that there is a large number of things, so remembering what is a problem. So I don't remember them at all. I keep referring to them. In fact, sometimes the definitions change over a period of time too. But the problems will help you remember some stuff. So if you are going to if you're going to do the problems and maintain the right programs and so on, uh, that will uh, that will help you remember the things. Otherwise, you'll just refer to them. And I mean, Wikipedia is pretty good in math actually. A lot of subjects not so good, but Wikipedia is excellent in math. So whenever you know a name, looking at Wikipedia is good enough to find out pretty much the correct thing. So we had a formula for it. R equal to 0 to k minus 1 raised for k minus 1 r raised for n over r factorial and k minus r factorial. And we had these Bell numbers. This was the number of ways to partition In into non-empty subsets. And this is essentially the sum, k going from 0 to n. And B0 was defined to be 1. So this was last time. Yeah.
For Stirling numbers, it's -1 to the power k minus r, right? Rather than k minus 1.
It's k minus r, if you say so. Okay. So we were at finding the formula for B of n. So let's do B of n. Is the sum of the Stirling numbers. So k going from 0 to n. And I'm going to go to infinity, because note that S and k is 0 for k bigger than n. So I can just sum this sum can be going from, sorry, k equal to 0. I mean, for most n, k equal to 0 is also 0. But it just helps to have going from 0 to infinity. And then we use this guy. That's the main reason why I got r equal to 0 term. And forcefully multiplied and divided, and then r factorial is 0 factorial is fine, and then this became 0. So r equal to 0 to 1 minus 1 raised per k minus r raised per n, r factorial. And this is a sum, and so you can look at it as a Cauchy product. And formally, the way I look at it is that we interchange the sum using some, so you draw some pictures of where the sum is. So this is a sum. This double sum is over all lattice points as shown. So what we do is we draw a picture, and let's say this is r, this is k. So for k equal to 0, r goes from 0 to k. So to draw this line, y equal to x, or rather r equal to k, then this is the region where it's going. So all the lattice points which are in this region are covered by this sum. And what we do is we interchange the sum. So we do, so here r is 0, then k goes from 0 to 0. R is, k is 0, then r goes from 1. Then k is 1, then r goes from 0 to 1. K is 2, r goes from 0 to 2, and so on. And here what we do is we switch it, and we go this way. So essentially, what we are doing over here is that we are going R first. So we are using this lemma. By the way, what I'm teaching you right now, this particular picture, is extremely important. So let's say this is AKR. Then you go R first, 0 to infinity, and K going from R to infinity, AKR. And then you can shift the index here. K going from 0 to infinity. So K is starting from R, so when can, and here it's starting from 0. So it is R plus KR. This is what you do. Do you understand this? Is this clear? This is what you do in double integrals. Is this okay?
Yes, Professor.
Okay. So we do this. In fact, Wilf calls this the snake oil method somewhere. So snake oil is something like I don't know, like Chawanprash. I mean, snake oil is supposed to cure everything. So he says whenever you're in doubt, you interchange the summation, like something like this. So if we do that, we get this sum, which was in green, is equal to, so Bn is equal to uh, r going from 0 to infinity. Let's just do k equal to r to infinity first, minus 1 raised per k minus r raised per n, r factorial k minus r factorial, and then I will shift the index. So basically k was going from r, and here now it's going from 0, so you replace k by k plus r. So this becomes k, this becomes, stays r factorial, and this becomes k factorial. And now one can take it out. So these are terms only involving k should stay in. So this is r going from 1 to infinity, and terms only involving k, that's minus 1 raised per k, or k factorial. And now this fellow right here is familiar, that's e raised to minus 1. So we get e raised to minus 1 summation r equal to 0 to infinity. So this is some kind of a weird formula for Bn, and we had so it's consistent with B0. So assuming you put n equal to 0 first, So it's consistent. Put n equal to 0 first. Because there's a problem with n equal to, with r equal to 0 then and so on. So first, if you just put b equal to 0, whatever you get, and then that works. Okay, so this formula is okay, but not so great. Anyway, we have some formula and it shows up with an e, so that is very interesting. That e comes up somewhere here. And what we want to do is, we want to, so there's a nicer formula. So we have a formula for b of n, which is this guy. So this is b of n. And I should be able to maybe highlight it. I used to totally hate people who use highlighters in books, especially if I have to read the book myself, but now I don't mind using the highlighter. Okay, so we find the exponential generating. So Wilf actually makes a makes a logic why you should use EGF and so on. In practice, I found that it rarely works. You just try everything. So you try this, you try that, and something works. That's all. So in the end, this you get a nice formula from EGF, and one doesn't know whether you can get something else from the other guys also. So let's find the, let's call Bx, let B of x be equal to B of n, x to the n over n factorial, n going from 0 to infinity. Let's find that. And this is raised power minus 1, summation n going from 0 to infinity, x to the n over this. So there is an r going from 0 to infinity, and so there is a r raised per n, x raised per n over r factorial, right? It's all right so far? So far, so good? Okay, so now we have another, now we don't need to do much. So we have, let's say, n and r. So when n is 0, then r is going from 0 to infinity, n is 1, r is going, so it's this region. And I just simply write it in the other way without doing much of it. This. So what this means is that r is going from 0 to infinity first, and then n is going left to right. So this becomes e raised power minus 1, r going from 0 to infinity, n going from 0 to infinity. I mean, these pictures are just to convince you that the pictures are just to convince you that we are the sum is over the same lattice point. So it's, r and n going from 0 to infinity in the plane should be the same, and you can interchange if you have some rules for convergence and so on, uniform convergence. In this case, everything is fine. So, well, 1 over r factorial, and what you have here, you have rx raised per n over n factorial. So this you know, right? What's the inner sum?
e to the power rx.
E to the power rx. And now this guy also you know. This is e raised per x raised to the power r over r factorial. So inside here, It's e raised per x raised per r over r factorial. So this also you know. If you knew the previous guy, then you know this one. So it's e raised to the power x, and the whole thing becomes e raised per x minus 1. So b of x is e raised per x minus 1. So that's a nice enough formula. This time you have two e's in it. All right so far? It's okay? This is fine? Shall we go on?
Yes, Professor.
Yes, Professor.
Okay, now there is this another technique. So we have a generating function. Just to summarize, I think I should put my coffee this side. So we had Stirling numbers. Then we had this expression for Stirling numbers, looks like hell. So, but if you sum it up, then we get some formula for B of n, which looks nice, but it's it's nothing. It's an infinite sum again, and not a nice enough one. But when we take the generating function, then generating function turns out to be nice. So, if you recall, we found it easy and convenient to calculate Stirling numbers by some recurrence relation. Okay, so in general, the philosophy is recurrence relations. So so general philosophy, I would say, the recurrence relations will give rise to generating functions, which are a little simpler maybe. And it could give rise to explicit formulas. So this happened in the case of Fibonacci, for example, or it could also lead to some more recurrence relations. So, or maybe easier. Let me not say easier, let me say nicer. Nicer recurrences. So this is a general theme. I mean, we start with a combinatorial object. We may want to find its recurrence relation. We want to know how to calculate it, right? We want to know how many there are, so we want to compute it or count it. Then one way of counting it is through recurrence relation. Sometimes it's okay to count from there, but we try out as generating functions. Generating functions may be simpler. They could be of two types. They could be OGF, EGF, and number theoretic context. There's a third type which we will do. And then these GFs may have explicit, may be simpler, certainly usually simpler, may have good forms, may have explicit formulas. You can manipulate them, and then go back and get a recurrence. So this is the example that I want to do. So how to get a recurrence from a generating function. Again, the idea, all ideas, I mean, one thing I found is everything goes back to Euler. Almost all ideas are in this domain are due to Euler. Euler was so I've written this somewhere that he was a master of Combinatorics. Have I introduced this term to you? So this is an invention.
Yes, Professor.
So Euler was a master of mathematics. So I've actually written this in a paper that Ramanujan was a master of mathematics in the class of Euler. So it's official word in a published document. I mean, it's been published 2-3 times. So I'm not the only guy. So how to get a recurrence from a general generating function, and what we do is we will get a generating function from for Bn from this, and the idea is this it's called a D. Um, so you take if this is a generating function, you take its log and then you take d by dx of the log. So you get basically you get f prime of x over fx equal to something, and then you take f prime x equal to this something times f of x, and from here you get the recurrence. So it looks. Let me begin with this guy. So we have b of x is equal to e raised per x minus 1. So we take log of e raised dx, which is e raised per x minus 1, and then we take the derivative. So b prime x over b of x is equal to e raised per x. So what is b prime x? B prime x is b of n x to the n over n factorial, its derivative. So that is um, we had an exponential generating function. So n is going from 1 to infinity. And this is equal to e raised per x b of n x to the n over n factorial, and n is going from 0 to infinity. So this right hand side is x to the n over n factorial, and so let's compare. Well, we know this guy also. We can write this as n going from 0 to infinity. So we can combine, if you recall, we had done this. Um, so this was k going from 0 to n choose k. Um, b of n minus k, I think, and times x to the n over n factorial. So let me verify where we had done this. Here it is. This guy. So in the remarks entitled tricks in the previous section, we had multiplied two exponential generating functions, and we got this answer that we got a binomial kind of convolution. Now in our case, we are just multiplying a of x, which is ak is 1, so we just get this guy. Right? We can just put bk here. So this was, let me just rewrite it using summation n x to the n over n factorial times right here. Dn x to the n over n factorial equal to summation Cn x to the n factorial. This is n going from 0 to infinity, n going from 0 to infinity, and Cn was summation n choose k, ak bn minus k. So our Cauchy products in this term And now we compare anyway. So we compare our coefficients. Compare the coefficients of x to the n over n factorial on both sides. So here, let's do x to the n. Yeah, so this is this should be n equal to 1, right? But there is something wrong here. This is a mistake. I think it's bn plus 1. I'm taking the derivative. So this is n going from 0 to infinity, bn plus 1 x to the n over n factorial. So when I compare coefficients of x to the n on both sides, I get b of n plus 1 is equal to, and now here I'll get summation k going from 0 to n, and choose k, bk. So n plus 1 is in terms of n plus 1 and below, and this is for n bigger than equal to 0, and b0 is defined to be 1, and using these two guys you can calculate. So this is a recurrence. This is a very practical, by practical I mean it's easy to implement recurrence relation for VM. Okay, any questions in this calculation?
Professor, small clarification. I didn't follow the n equals 1 to n equals 0 part.
Sorry?
In the summations, I didn't get how we got from the n equals 1 to n equals 0 at some stage.
Which summation?
In the first line, after the log, yeah.
Here?
Yeah.
Yeah. So I sort of hurried through that. Let me just write it. So we had seen this before. So b of x, let me just do it in a different color here. So b of x is what? It's b0 plus b1 x plus b2 x square over 2 factorial, so on. So if I take the derivative, this term goes away and I get b1, and then I get 2 times x over 2 factorial. So I get b2 times x plus b3 times x square over 2 factorial, and so on.
Yeah.
So I'm essentially starting from 1, and that's the reason why this happens. But anyway, so this is the reason why this happens. But coming back to this, I mean, you've taken term by term differentiation here. So this is another way. I'll say I'll take the derivative d by dx of summation bn x to the n over n factorial, n equal to 0 to infinity, and first term has to be 0. So I start from n equal to 1, and then I get bn n times x to the n minus 1, and because the n cancels. And then I can just shift the index. So this is 1, so I want to start from 0. My 0 looks like 1, of course. So now if I want, so the first term is 1, but I'm starting from 0, so I will add n to everything. I'll add 1 to all the n's. And that will give me this thing. Does that clarify? Dhruv?
Yeah, thanks.
So you need to get more multicolored pens. Combinatorics guys get multicolored pens because they keep doing different colors. Well, and they do make messes like this, which is difficult for normal students. Okay, so let's go back to green. So you can implement this and see if it works out. And now I want to connect with the Stirling numbers of the first kind. So the Stirling. So this is also related. This is related to your homework problem. So which I haven't graded yet. A small SNK. So Stirling found both of them, and this is what we want to do now. The combinatorics of Stirling numbers of the first kind we will do next. I mean, after we finish with this, or maybe after a couple more items. But I want to because that has to do with permutations. So that's a largish area, and it requires more efforts to do. I mean, there are many things one needs to do in this thing. So I still have to decide whether I do it next or should I do it a little later. But anyway, it's important to do permutations because we also want to do determinants at some. To come back to our paths problem, there's a nice determinant theorem. So we need to know more about permutation. So anyway, but that will happen later. But let me connect here. So recall your homework problem. So x sub n was written as this is small snk x to the k going from 0 to infinity. Okay, and this was a rising factorial x plus n minus 1 for n bigger than 0 and 1 if n is equal to 0. So this was the Pockhammer symbol or rising factorial. So I should mention that Knuth, Graham, and Patashnik, they use something like this, x to the n with a bracket on that, for rising factorials. And they use something like this for falling factorials. And I'm not sure what Wilf also might be using these things. So they were friends, I guess. So, but this is not standard. This is standard. In fact, this has come from the special functions world. So this has been around for many years. But this is sort of in the combinatorial world. But these two objects are the same essentially. So what are falling factorials? Falling factorials, you do what you're doing like this. And one can just take out n here and you get minus n plus minus x plus 1 minus x plus n minus 1. So this is minus x sub n. So they are both equivalent.
Professor?
Yes.
Just a quick question. What exactly are special functions that you mentioned?
Special functions are, I mean, it's an area of mathematics. Basically, any functions which are special enough to be called by some name. So if they appear somewhere, they're called special functions. So, yeah, I don't know how to say it. So exponential function is a special function, gamma function. All functions, Bessel function, anything which comes up which is important enough to be called by some name, that is called special function. So there's a whole area of mathematics which I'm part of, which is called special functions. And basically we study special functions. They're special. It's like, I told you the combinatorics definition, right? It's combinatorics that counts. So similarly, special functions are special, and they are related, both of them. So they come up everywhere. I mean, physicists and everybody knows about them. So, Bessel function, for example, you'll see a lot. And so people like Euler, Jacobi, everybody did all this stuff, and they use this notation. So once it's there, then it's there. And this is a new notation, and then later on somebody found out that they're the same. So essentially, Knuth in his book, so this is an aside, so I would say this is gossip. So Knuth in his book, he has a million ways to find binomial coefficient type. Right. So then the thing is that since the last century, people know something called, so we might do this, something called hypergeometric series identities. These are from Gauss's times, and there are about like a handful of them. So then somebody pointed out to Knuth that, look, all these millions of binomial identities are special cases of a handful of hypergeometric identities. So this was, there's a chap called Ranjan Roy. He wrote an article in Monthly. Pointing this out to Knuth. So Knuth already had written his books, in his 60s and all, in 68, 70, and he had a huge number of techniques for handling, very clever, because, binomial coefficient identities come all over the place in computer science. So he was doing that. And then wrote an article. Then in GKP, Ram, Knuth, and Patashnik, which is concrete math. Then these guys, Knuth and Graham and others, they included a section on hypergeometric function, saying essentially that once you understand this notation, you don't have to do that. So there is some collision of these two words which happened. They realized, combinatorialists realized that when they are dealing with generating functions, they're dealing with functions, and special functions, people know a lot of tricks about how to operate with functions. So for example, this trick that I've told you, which is a trivial trick actually, this kind of trick is very much up, say, a guy who does double integrals or double sums. But computer scientists found it hard to handle. So it took a while before they could start operating. But it gets used all the time. So anyway, so I hope I've answered your question. So there is a special function seminar that we operate, and it's quite wide-ranging. I mean, all kinds of people come, including people from combinatorics. Anyway, so we calculated this guy, and here is the problem. The problem is an inverse problem. So this color I'm using more for highlight. So the inverse problem is to write this in terms of this guy. So what are F and K? And this is again a very important problem and a general technique. So that's why I want to do this in. So yeah, so this is a special functions approach. You do one example, and that example sort of generalizes to million cases. So this, but this is also a combinatorial technique in some sense. You don't believe in grand generalities. if we do a few well-chosen examples, and then those examples can generalize. That's the idea. So it's anyway. So what am I saying? What I'm saying is that this guy xk. What is xk? Xk is 1 for k equal to 0. Then x, then x plus 1, then x, x plus 1, x plus 2, and so on up till n terms. This well, this is for k equal to 0, 1 up till n. So this is a set of polynomials of degree k, okay, for k equal to 0, 1, 2, whatever, and therefore is linearly independent uh, in the vector space of all polynomials of degree less than equal to m. So forms a basis. I mean, what is a vector space? Vector space is this set. So I think linear algebra was a prerequisite. So everybody knows vector spaces, right? I mean, I don't know them so well, but I hope all of you know them quite well. Is everybody familiar with what is a vector space?
Yeah, I think we're all familiar.
Okay. So, I mean, there is, so you have polynomials, there is a plus and there is a scalar multiplication. Okay, so we are not multiplying the things and then this happens. So what are we saying? What we are saying is that in this basis, you can write any polynomial of degree n. And in particular, so in this basis, one can write any polynomial. So in particular, we can do x to the n. Can be written like this, as indicated. Yeah, and so it's an inverse base. It's a basis transformation matrix in some sense, and then you can extend it to by induction. You can extend it to infinite degree thing. So you can extend it to all the vectors, all polynomials basically of finite degree. Right. So anyway, in any case, this is the problem we want to solve, and we will solve it in exactly the same way as you must have done your homework problems. So, I mean, I hope you did it this way. So we write x to the n plus 1 in two ways. And this is x times fnk, x to the k going from 0 to n. And this guy right here is fn plus 1k, x to the k going from 0 to n plus 1. So this chap is k going from 0 to n, fnk, x to the k plus 1. And what do we get? We get, so compare coefficients of x to the k. We get fn plus 1 k is equal to fn minus 1. Oh, wait a second, what am I doing? I need to do some. In technical terms, it's called Kalatari.
Let's put the line on top.
Huh?
Can use the other notation and put the line on top.
Which line on top?
Of the superscript. You said some other people use a different notation for the same.
Yeah, I don't like it, so I don't use it. I mean, it's, yeah. It's a, I mean, these guys are popular. You're going to see that book a lot. If you're going to do computer science, you're going to see it. So I need to tell you what it is. But if you read a paper nowadays, nobody uses it. I mean, I used it in papers, but nobody uses it now. So it's a little old-fashioned, I would say. Anyway, so what I'm saying is that this is equal to x to the k. So what I'll do is I will write this x. Okay, let me do this carefully. So this term right here is x plus 1, x plus 2, so on, k terms. So the last term is x plus k minus 1. So this x right here, I'm going to write as x plus k fn k x sub k, k going from 0 to n, and then I will subtract the k going from 0 to n fn k x to the k. And this will give me k going from 0 to n f n k x to the k plus 1 minus k summation f n k x to the k. And I delete all this business. All right, so far, so I replace this x by x plus k minus k. That hardly takes any problem. Yeah? Is that okay?
Shouldn't the k be inside the summation because it's not defined?
You're right. So, what do I erase? I think I erase this.
Professor?
Hang on, let me fix this first. Okay. Okay, this color went bad. So I have k going from 0 to n, x plus k here, minus k times this. And this guy is also wrong. Yeah, now it's okay. Okay, there was a query. Is this okay now?
Yes, Professor.
Okay, so now what are we comparing? Now we compare coefficients of x, and this side is also something wrong. Sorry about that. So we compare coefficients of x sub k, so the Pockhammer symbol, and then we get fn plus 1k is equal to, now here I'll get n k minus 1 minus k times fn k. Yeah. And this was for, well, yeah, let's just look at this somewhere in the middle terms, you know, when n is bigger, when k is, k could be 0, I suppose, but no, k can't be 0 because I have a k minus 1 here. So this should be for k bigger than 0. And one can find other items like we did earlier. So this we can find directly from definitions from here, from star. So x to the 0 and x to the k, it's going to be 1. Then f of, so why is this true? So we want right? So n is equal to 0, 0 to 0. So the first term has to be, I mean, this is 1. So, and x sub 0 is also equal to 1. So there's only one term here, f00, 0, and times 1. So we get this is true. We can get fn0 for n bigger than 1. What do we get? So we have x to the n, and we want the first term. So this is equal to fn0 x sub 0 plus fn1 x sub 1, so on. Now this is a constant. This is 1. So there's no constant term here. So it's bound to be equal to 0. So that's fine. Then of course fnk is equal to 0 for k bigger than 1, k bigger than n. This is obvious from, I mean, this is obvious because the degree of the x sub k cannot be bigger than the degree on the left hand side. So we have, again, we have x to the n is on k, fn k, x sub k. So of course this k cannot be bigger than n. That's why we are going from 0 to n. Okay, is this fine? So recall which color? This was Sn minus 1, k minus 1 minus k s n minus 1 k plus. Remember this guy? And if you replace n by n plus 1 in this, you will get n plus 1 k equal to Sn k minus 1 plus k times Snk. So almost the same as this chap, right? Okay, so let's look at.
So there is this minus sign in here, plus sign, I guess.
Exactly, exactly. So this is the only problem. This is the only challenge. Rest, almost everything looks the same. These special cases are the same and so on. So let me, I want to calculate fnk, and I think it's the same thing as Stirling numbers except with some plus and minus signs. So let's let gnk be this. Then from this guy, right? So if you multiply this chap by minus 1 raised to the power, if you multiply this double star by minus 1 raised per n plus 1 minus k, then what do you get? You will get minus 1 raised per n plus 1 minus k, f n plus 1 sub k is equal to minus 1 raised per n minus k minus 1. It's the same thing, fn k minus 1. And here you will get minus, you get plus minus 1 n minus k f of n k. So this guy right here is your gn plus 1k, is equal to G and K minus 1 plus, and there's a K here, K, G and K. And these things will work. Gn0 is equal to 0 for n bigger than 0, and Gn k is 0 for k bigger than 1. So these follow from this guy. So we have, so Fnk is equal to minus 1 raised per n minus k Gnk, and Gnk we know is capital S. All right, so what have we found? Any questions on this calculation? I mean, I could have, we could have started with minus signs there, and so there was some confusion. So, but I wanted to just get this straight away. So, what have we done? We have shown x raised per n is equal to summation k going from 0 to n minus 1 raised per n minus k capital Sn minus k x sub k. And of course, you already had x sub n is equal to k going from 0 to n small s in k x to the. Yeah. In the assignment 1, we had this thing. Yeah? Is this fine? This is okay?
Yes, Professor.
Professor,
Yeah. Yes, Preetham?
Professor, am I audible, Professor?
Yeah. Go ahead.
So, does it mean that if we take the inverse of this matrix S and K, small s and k, we'll get the other matrix, which is minus 1 to the power n minus k, capital S and
Yeah.
capital K?
Exactly. So you took the words right out of my mouth. So what this means is, so this is Preetham's observation. This means that the matrix or the matrices S and K for nk going from 0 to infinity and minus 1 raised per n minus k S and k going from 0 to infinity, not, are inverse. So let me just say this is like a, I mean, they are, so of course, what this means is that for any n bigger than 0, Snk, nk equal to 1 to 0 to n, and minus 1 raised per n minus k, Snk, nk 0 to n are inverses. So by saying that the infinite guy is an inverse, I mean this is true for any n formally. And note that Snk is equal to capital Snk, they look the same, is equal to 0 for k bigger than n. So n is rows, k is bigger than n, this is 0, right? So they are lower triangular matrices. Okay, and in fact, normally this is not the way they write it. So normally you write it, so we claim that capital S and K, n k equal to 0 to infinity, and so we can move the minus signs to the other way. These are called in the in the literature, these are called signed Stirling numbers of the first kind. So they are sometimes also called C and K. So you see, I mean, Stirling numbers of the second kind don't usually come with signs. The Stirling number, the first kind, comes with signs. But in our scheme of things, if I'd given you that as a homework and derived this first, then you would have got this. This is you already have written a program for binomial coefficients. You can write a program for this to just verify this, to find the inverses. It's beautiful that this happens. Let me just show you how to do this. So there's a nice trick. Um, let's call this. I'll just show it to you. So let's say minus 1 raised to power n minus k, capital S and k is an element here. And what I do is I multiply on this side by a diagonal matrix. So I multiply by minus 1 raised to 0, minus 1 raised to 1, and so on. So suppose I multiply it, what happens? So I multiply this guy, this is the nth row, with this guy, right? So the only term in the nth, so I'm multiplying by some whatever I'm multiplying, the nth row term gets multiplied by minus 1 raised to n. So this disappears. And on this side, I multiply by minus 1 raised to k, which is the same matrix. I mean, it's minus 1 raised to 0, minus 1 raised to 1. And if I multiply any term here by this guy, then the kth column term, all of them get multiplied by minus 1 raised to k. So whatever this matrix is also the same thing as the small s and k matrix with the 1 minus 1, 1 whatever here, 1 minus 1, 1. And the inverse, so if S and K matrix, the inverse is, so what is the inverse of, let's call this DL, and let's call this DR. I mean, they're the same. This is DL and this is DR. So what's the inverse of this guy? This is DR inverse, S and K inverse, and DL inverse. And DR inverse is the same thing, minus 1 raised to n. This inverse is small s and k, and this is the same thing, minus 1 raised to k on the diagonal. And this will give you minus 1 raised to n minus k, small s and minus. So yeah, so anyway, I hope this is clear. So this, I mean, this is a common trick in the business to multiply on the left and right, and I might have got a little confused, so work it out. See if indeed multiplying by the left guy gives you terms only depending on n, and terms only dependent on k, you multiply by a diagonal. So maybe verify this remark. It's a useful trick to know. If you multiply by a diagonal matrix on the left, then it changes elements in the nth row. This is a very undiagonal matrix, let's say Dn, and it changes in the element row by multiplying by. Okay, let me formulate it properly. Let DL be the diagonal elements of Dn, right? So this is basically D0, Dn, so on. And let A be a matrix A and K. Then DLA will be DNA and K. So verify. I mean, I may be wrong. And similarly for DK, D right. A DR would be A and K D. So I may have flipped them. I don't think I have, but just verify. Either way, the proof works. So this is how it's usually stated. Let me. So it's usually stated as S and K and -1 raised to n minus K. S and K are inverses. Okay, any queries so far? Yeah.
Just a small clarification. The second S, like the -1 to the power S, -1 to the power n minus K, S and K, the second S is the Stirling number of the first kind, right? It's still the second kind.
No, first kind.
Right. Thank you.
Yeah, first kind. So the connection is yeah. So one is the first kind, one is the second kind. Yeah, they look the same, don't they? So in general, this is also something which is very interesting. Is that this implies what are called inverse relations. So let Fnk and Gnk be infinite lower triangular matrices. Okay, and let AK and VK be sequences. These are inverse. That are inverses of each other. Let AK look at all like K k be sequences such that um, Bn is equal to Fnk Ak, then An has to be Gnkp. Okay, so these are called inverse relations. Right? So uh, now when you have a matrix transformation, that is a specific example of inverse matrices. So we found inverse matrices, right? Earlier we had a specific, we had a polynomial going into another polynomial basis. So it was a specific matrix, but in general it proved that those two matrices are inverses. So um, uh, in particular, um, we have if an is equal to, or rather, if we put bn, n going from 0 to infinity, of capital S N K A K, then we must have an equal to small s n k. So these may be very different looking things. See, so so there are millions of identities, and a lot of the identities are the same. This was pointed out by Riordan in his book. So there's a book by Riordan, which is a classic, which is I suppose it's available from somewhere. And he talks about these inverse relations, a lot of identities which look very different, but they are actually the same if we write them like this. And again, I want to just before closing, we have 10 minutes, right? Recall your homework problem. So you had Fn k is equal to n choose k, and your guess, what is your guess? Is that what you guessed? So when we had a matrix of binomial coefficients and we took its inverse, were you getting some salt and pepper look, something like this?
Yes, Professor.
Did you get that in your
Yes,
homework?
Professor.
So this is a typical example of inverse relations, right? So how do we prove this? So we recall, I think you might have proved it already because you were supposed to prove it. But anyway, here's a proof that I have. Right? And then we simply say replace x by x minus 1 to get x raised per n is equal to k equal to 0 to n choose k, x minus 1 raised per k. Now replace x by minus x to get minus 1 raised per n, x raised per n equal to k going from 0 to n, minus 1 raised per k, n choose k, x plus 1 raised per k, and this implies that x raised per n is equal to now comparing 1 with 2, find that and choose K, this matrix is and are inverses. So if AN and BN are such that Bn is equal to n choose k, ak, k going from 0 to n, then an is equal to so well, this is any questions on this calculation? Is that how you did it?
No, Professor.
Okay, so I'll find out how you did it. But anyway, this is one proof, and um, it's a fairly easy proof. And this thing, we will see it again. So this result, um, this result is known as principle of inclusion exclusion. And I need to I need to do more terminology, so we will encounter it again. We will come back to it at some point. I mean, uh, it's a bunch of things basically. It's this principle. I mean, it's so simple. If you look at it, all it's saying is that you take this matrix and you invert it, and you get the same matrix with, negative signs. And the proof is virtually trivial. I mean, it follows immediately from this thing. I mean, you could multiply those two and do all kinds of stuff. But so you found a proof. I hope everybody found a proof, right? Everybody got a proof of this result, right? Yes? Any homeworks? I, I mean, you're supposed to answer.
I guess, Professor.
Okay, everybody.
Yeah, yeah, Professor. We proved like the matrices were inverses of each other. That one we proved.
Okay, so you directly proved it. But anyway, the point is this result is virtually trivial, but it's a very deep result.
Yes, Professor.
This particular result, that these two are inverse matrices, and it is known as the principle of inclusion exclusion, and it's known as a sieve method, and it's known as Mobius inversion. So in different contexts, it's known as Mobius inversion. We will see all those contexts, and it's also known as I don't know what it's known as. It's, sieve methods. So it's at the heart of what are called sieve methods. Sieve methods in number theory. It's a very, very elementary kind of thing, but it's extremely useful. And as you can see, I mean, it's all about inverting two matrices. That's it. And uh, before closing, let me just say, I mean, what are we doing really? I mean, here we are just solving a bunch of equations. That's it. So this is a specific solution, but here we are just solving some equations. I mean, B0 is equal to A0, B1 is equal to, uh, you know, uh, n choose 0 plus 1 choose 1, b a0 plus a1, and b2 is equal to this, you know, writing in terms of a1, a2. So it's a triangular system of equations that you're solving. That's all. And you're writing an's in terms of the b's. That's all you're doing. So we are solving a system of equations, of linear equations, and the simplest kind, I mean, which is a triangular system. I mean, it's so trivial that you hardly bother about in linear algebra. This is the simplest thing, simplest case. So, but it's of tremendous importance. Okay, that's it. Any questions?